Connecting a generator neutral in a standby system requires careful consideration to ensure proper bonding and safe operation. The approach you're considering is correct. The generator neutral should be connected to the same location as the main feeder neutral, which is typically the main bonding jumper within the main breaker section of the switchboard. This ensures the generator neutral is appropriately bonded to the grounding system. To summarize the steps for connecting the generator neutral: firstly, bring the generator neutral conductor into the switchboard enclosure. Secondly, connect the generator neutral conductor securely to the main bonding jumper. Thirdly, verify that the generator neutral is also effectively bonded to the ground bus and the grounding electrode conductor, also known as the GEC. This comprehensive connection process ensures the generator neutral is correctly integrated into the grounding system, promoting safe and reliable operation of the standby power system. It's important to remember that the main bonding jumper is the critical link between the neutral conductor and the grounding system, the service equipment. It is what ensures that any fault current has a low impedance path back to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. When the generator is operating, it becomes the source of power, and therefore its neutral must be bonded to ground at the same point as the utility service neutral. This maintains the integrity of the grounding system and prevents the development of dangerous voltage potentials. Without this bond, the generator neutral would float, and any fault currents might not be properly cleared, posing a significant safety hazard. Grounding electrode conductors are conductors used to connect the equipment grounding conductor, the grounded conductor, or both, to one or more grounding electrodes. This provides a path for fault current to return to the source and helps to stabilize voltage to ground during normal operation. The size of the grounding electrode conductor is determined by the size of the service entrance conductors in accordance with NEC Table 250.66. The grounding electrode conductor must be connected to a grounding electrode, such as a metal underground water pipe, a ground ring, or a rod or pipe electrode. If a metal underground water pipe is used as a grounding electrode, it must be supplemented by another electrode, such as a ground ring or a rod or pipe electrode. Grounding electrode conductors are essential for safety and must be installed properly. They must be continuous and securely fastened. They must also be protected from physical damage. The grounding bus is a terminal strip within an electrical panel that serves as a central connection point for all grounding conductors in the system. It's typically a copper bar securely mounted within the enclosure. Grounding conductors from branch circuits, equipment, and other metal enclosures are all connected to this bus, providing a low impedance path for fault current to return to the source. This connection to the grounding bus ensures that any fault current will quickly trip the circuit breaker or fuse, minimizing the risk of electrical shock or fire. The grounding bus is, in turn, connected to the grounding electrode conductor, which runs to the grounding electrode. The grounding electrode provides a direct connection to the earth, further enhancing the effectiveness of the grounding system. The size of the grounding bus and the grounding conductors connected to it must be sufficient to handle the potential fault current. The National Electrical Code, or NEC, provides guidance on the proper sizing of grounding conductors and grounding buses. The NEC is a set of standards that is used in the United States for the safe installation of electrical wiring and equipment. It is part of the National Fire Code series published by the National Fire Protection Association, or NFPA. While not itself law, the NEC is commonly adopted by states and municipalities in an effort to standardize their enforcement of safe electrical practices. In some cases, the NEC is amended, altered, and changed at the state or local levels. The NEC covers a wide range of topics related to electrical safety, including wiring methods, overcurrent protection, grounding, and equipment installation. It is updated every 3 years to reflect changes in technology and to address new safety concerns. Compliance with the NEC is essential for ensuring the safety of people and property. Electrical installations that do not comply with the NEC can be dangerous and may be subject to fines or other penalties. The NEC is a complex document, and it is important to consult with a qualified electrician or electrical engineer to ensure that electrical work is performed in accordance with the code. The equipment grounding conductor, also known as the EGC, is a critical safety component in electrical systems. It provides a low impedance path for fault current to return to the source, which allows overcurrent protective devices, such as circuit breakers and fuses, to quickly trip and clear the fault. Without an effective equipment grounding conductor, fault current could flow through unintended paths, such as metal enclosures or equipment frames, creating a shock hazard. The equipment grounding conductor is typically a wire, but it can also be a metal raceway or other approved conductor. It must be properly sized to handle the potential fault current and must be securely connected to all metal parts of the electrical system that are likely to become energized in the event of a fault. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit, in accordance with NEC Table 250.122. The equipment grounding conductor must be run with the circuit conductors and must terminate at the grounding bus in the electrical panel. In addition to providing a path for fault current, the equipment grounding conductor also helps to reduce electrical noise and interference. By providing a low impedance path to ground, the equipment grounding conductor helps to shunt away unwanted electrical signals that can disrupt the operation of sensitive electronic equipment. The NEC addresses optional standby systems in Article 702. An optional standby system is a system that is intended to supply power to designated loads in the event of a utility power outage. Optional standby systems are typically used in applications where a power outage would not pose an immediate threat to life or safety, but would still cause significant disruption or economic loss. Examples of optional standby systems include systems that power computer networks, telecommunications equipment, and manufacturing processes. Because these systems are not legally required for safety purposes, the NEC provides more flexibility in their design and installation. However, it's crucial to ensure that the generator neutral is properly bonded to the grounding system and that all applicable codes and standards are followed. Key interlocking is a safety measure used to prevent the simultaneous operation of two or more pieces of equipment. In the context of a generator and main breaker system, key interlocking ensures that the generator breaker cannot be closed while the main breaker is closed, and vice versa. This prevents the possibility of backfeeding power into the utility grid, which can be dangerous for utility workers and can also damage electrical equipment. Key interlocking systems typically use a mechanical key that can only be removed when the breaker is in the open position. The key is then used to unlock the other breaker, allowing it to be closed. This ensures that only one breaker can be closed at a time. Key interlocking systems are commonly used in critical applications where safety is paramount, such as hospitals, data centers, and industrial facilities. The specific requirements for key interlocking systems vary depending on the application and the local electrical codes. However, the basic principle remains the same to prevent the simultaneous operation of two or more pieces of equipment that could create a safety hazard. A transfer switch is a device used to transfer electrical loads from one power source to another. In the context of a generator system, a transfer switch is used to transfer the load from the utility power to the generator power in the event of a power outage. There are two main types of transfer switches: automatic and manual. An automatic transfer switch, also known as an ATS, automatically senses a power outage and starts the generator. Once the generator is up to speed, the ATS automatically transfers the load from the utility power to the generator power. When the utility power is restored, the ATS automatically transfers the load back to the utility power and shuts down the generator. A manual transfer switch requires a person to manually switch the load from one power source to another. In the event of a power outage, a person must manually start the generator and then manually switch the load from the utility power to the generator power. When the utility power is restored, a person must manually switch the load back to the utility power and shut down the generator. Transfer switches are an important part of a generator system, as they ensure a smooth and reliable transfer of power in the event of a power outage. The type of transfer switch used depends on the application and the level of automation required. The size of the transfer switch must be sufficient to handle the load being transferred. The transfer switch must also be properly installed and maintained to ensure reliable operation. In addition to following the specific steps outlined, it is essential to consult with a qualified electrician or electrical engineer to ensure that the generator neutral is properly connected and that the system meets all applicable codes and standards. Improper installation can create a dangerous situation and could result in equipment damage, electrical shock, or fire. In summary, to safely connect a generator neutral conductor, firstly, make sure to bring the generator neutral conductor into the switchboard enclosure. Secondly, make sure to connect the generator neutral conductor securely to the main bonding jumper. Thirdly, verify that the generator neutral is bonded to the ground bus and the grounding electrode conductor. Consulting with qualified professional electrician and electrical engineer would be a proper method of completing a safe and reliable electrical connection.